discussing the applications of equilibrium constant, and the previous video we discussed the uh, predicting the extent of a reaction. Okay, and now in this video we are going to discuss predicting the direction of a reaction. So if at a certain time, let us say we know the concentration of reactant and product. Okay, concentration of both reactant and product at some given time. Based on this value, we can predict, if we know this concentration at some given time, we can predict if it is going to be a forward or a backward reaction. Okay, so let us, because at equilibrium the reaction is proceeding at the same rate. If it is some other time which is not the time at equilibrium, it can be before that or after that. So depending on the time, the reaction will proceed either in the forward or backward direction. How do we predict that? If you know the concentration of the reactants and products at some given time, which is not the time when equilibrium is established. Okay, and to predict this, we use a term called as the reaction quotient, that is QC. Till now we knew about Kc, equilibrium constant. This is called as the reaction quotient, which also can be expressed as QP or QC. QC is the reaction quotient in terms of concentration, reaction quotient in terms of pressure. And what is this reaction quotient in terms of concentration? It will be the same thing. If you have remember my general reaction, this was my general reaction. It will be the same thing here. Okay, product of the concentration of the products 2 raised to their stoichiometric coefficients to the product of the concentration of reactants raised to their stoichiometric coefficients. Now this very much resembles Kc. If you remember, Kc was also the same. Okay, so Kc, this is the definition of Kc. This is the definition of Kc. What is the difference here? This Qc is at any other time other than equilibrium, and this Kc is at equilibrium, means concentration at equilibrium. Okay, so the only difference, it is exactly the same. This is calculated when, what are these concentrations? Concentration C, D, the concentrations of the reactants and product at equilibrium. Here the concentrations will be at any other time. Otherwise they are the same. Okay, if you talk in terms of definitions, it is the same definition, but the only change here is the concentration at the given time. Okay, now let us say okay, now let us say, suppose if Qc is greater than Kc. Okay, now we would know the concentrations, right? At a given time we would know this, and knowing this, if I calculate Qc and my Qc value turns out to be greater than Kc, what do you mean by that? Now just compare. Qc greater means the concentration of product is greater. Concentration of product at that time is greater than the concentration of product at equilibrium. So now Qc is greater. Look at that. This is having some fixed value. Qc greater means product is greater. Concentration of product is greater. Or this is smaller. But let us focus on one thing. Now if the concentration of product is greater at a given time, that means more product is formed. It has to now, the actual desired product if at equilibrium should be this. Now there is more product which is formed, so the reaction has to be in the backward direction. So as a simple rule, if Qc is greater than Kc, it's in the backward direction, and if Qc is less than Kc, what does it imply? Qc is less, that means you can say that reactants is now more. Okay, so the concentration of reactants is more at that time and is more at the time in comparison with, or concentration at reactant at time is greater than concentration of reactants at equilibrium. Okay, at the given time reactant is more. That means ideally at equilibrium it has to reach some value. But now it is the reactant is having a greater value, and to reach this value it has to consume that reactant. So it will proceed in the forward direction. Alright. And when, let me write the third case here. I will write it here maybe. Third one, if QC is equal to KC, then it means it is at equilibrium. The time when you have measured is exactly the time when the system is at equilibrium. Okay, so in terms of chart, if you want, there is a chart in your textbook which says that, you know, the same thing, whatever I have mentioned. Let us say this is QC, KC, this is QC and KC, and let us say this is QC and KC. Okay, so QC is greater, that means it's in the forward direction. This is in equilibrium, so this is backward direction, and QC less, that means it's in the forward direction. Okay, I'll give you an example so that it makes things clearer to you. I have the worked example 7.7. Okay, so there is a reaction given to you, 2A, which is getting converted into B plus C, and Kc for the equation is given to you, 2 into 10 power minus 3. Okay, so at some given time, you know the concentration of A and B and C are all equal at some time, and it is equal to 3 into 10 power minus 4 molar. Okay, you have to say what is the direction in which the reaction proceeds. Is it going to be a forward direction or it is going to be a backward direction? Okay, so yes. So Kc is already given. I just have to find Qc here. What will be Qc here? The concentration of the products here and reactants raised to the power 2 here. So concentration of everything is given to me. Right, so it is minus 4 multiplied by 3 into 10 power minus 4 divided by 3 into 10 power minus 4 whole square. And if you see this is the same power, everything is going to be cancelled out and it is 1. Okay, so that means what is it? Qc is 1 here and Kc is equal to 2 into 10 power minus 3. It is a lesser value. Qc is greater than Kc. That means it's in the backward direction. Okay, I hope this is clear. So we are done with 2 applications. You can predict the extent, means how much it can proceed, and this in the second application, at any given time, if you know the concentration, you can predict whether it's going to be forward or backward. If Qc is greater, it will be in the backward, because Qc greater indicates that product formed is greater, so it has to go back. Okay, and if Qc is lesser, then it will proceed in the forward direction. Okay, now the third application here will be calculating the equilibrium constant. Okay, so I will explain this. What is the meaning of this third application, calculation the equilibrium constant, equilibrium concentration, sorry. The concentration during when equilibrium is established. The third application is calculating the concentration at equilibrium. Okay, now I think the best way, there are a few steps given in your textbook, but you can just go through it. I believe you will understand it better if I actually take a real-time example. Okay, so I am going to do 7.9, and with this example we are trying to understand the application, this application. How do you find the concentration of reactant and product when equilibrium is achieved? Okay, so let us see. 3 moles of PCl5 kept in 1 liter closed vessel is at equilibrium. Okay, this is at equilibrium at 380 Kelvin. Calculate the composition of mixture at equilibrium. So Kc is given to you as 1.8. You have to find the concentration of the mixture at equilibrium. That means concentration of mixture at equilibrium. That means once equilibrium is achieved at whatever time, during the equilibrium state, what is the concentration of reactant, what is the concentration of product. And they have also given you the reaction. It is something like this. You are getting PCl3 plus Cl2. It's already balanced. Okay. So whenever you want to find the concentration of equilibrium, first step is you have to make sure it is balanced. You can go through the steps which is there in your textbook. Second, you have to write a column wherein you have that initial concentration, number of moles per liter or whatever dissociated, and concentration at equilibrium. We are going to make 3 sections here. Okay, initial is given to you. 3 moles you had taken and initially there was no product, so this is 0, 0. Let us say this number of moles dissociated is always x per mole, correct? So initially there were 3 moles, x moles of the reactant got dissociated. So x moles got dissociated, okay? And at equilibrium, how much it will be? 3 minus x, because out of 3, x moles got converted into product. So this is x and this is x. This is at equilibrium. Okay, when equilibrium was achieved, out of 3 moles, let us say x moles got converted into products. So here you have x, and out of 3, x moles got dissociated. So it is 3 minus x here. Now it is very simple. You just have to solve it. It is concentration of PCl5 into this is PCl3 into concentration of Cl2 divided by PCl5. Okay, and this Kc is given to you. It is 1.8. What is these two? X into x divided by PCl5, which is 3 minus x. Okay, now you just have to solve it. You will get a quadratic here. I'll just write the quadratic equation. If you cross multiply, plus 1.8x minus 5.4 is equal to 0. Okay, so if you just solve it, you're going to get x value as 1.5. That means the concentration of PCl3 and concentration of chlorine at equilibrium is this much, and the concentration of PCl5 is 3 minus 1.59. That will be 1.4 mole. Okay, now see, that's why I said it doesn't matter. You have taken 3 moles initially. So it all depends on the kind of reaction. It is not like this is 1, this is 1, this is 1. If this is 1.59, this also has to be 1.59. No. Alright, I hope this is clear. Yes, so that is how you use equilibrium constant to predict the extent of a reaction, predict the direction of a reaction, and also to know the concentration of the reaction mixture at a given at equilibrium.